Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the lecture 18. So most probably this will be the last lecture of state space. Okay, this has been a long journey for state space, right? I hope you are with me. Okay, I have tried to make the subject as much simpler as possible. Okay, so that you can understand all the concepts, right? All the concepts from like basic level to the advanced. I have given you all the tricks there. So if this is within the time limit, so I will try to finish the lecture within this lecture only, or it may so happen I have to add another lecture. Okay, that also may happen, but most probably this will be the last lecture of state space. Okay, and in this lecture we will study the principle of duality, what is stabilizable and detectable systems. These two are basically theory. Okay, MSQ or some theoretical question may come. Okay, so theory you need to know, and obviously questions will solve all questions from all the topics all over the place, right? Not too many, but most of the questions, this will be mainly not the gate PYQs. Okay, mainly questions from where I got, right? Okay, so like before starting the lecture, one thing I wanted to mention is, like in one of the cases I told you, right, the rank of the transpose and the rank of that same matrix is same. Now I told you the condition that it should be for square matrix, but I forgot actually it wasn't that condition. It can be for any matrix, right? It can be for any matrix. So let me find that condition where I wrote, so I will delete it actually. Okay, where is it? Okay, I don't find it. Okay, I will find and come back. Yeah, I found it actually. It took me a while. So here, right, I told you that rank of A and rank of A transpose will be same, but I forgot actually it wasn't for like only square matrix. It is valid for all of the matrices, because like what does rank mean? It means the minimum number of independent rows or columns. So whichever is minimum, right, that we will choose. So if I just switch my rows into columns, then at this stage, if my number of independent rows minimum were 2, then that will go to number of minimum independent columns, okay, or row, whatever, like they will get switched. So my rank will still remain same. I actually just in hurry, I maybe I wrote there A is a square matrix, so A can be any matrix, okay, but still in our case it's square matrix, so it is valid anyways, but still I thought of to like about mentioning it. So that was one thing. Okay, another thing was I gave you a few homeworks, right, to solve the questions, okay, using Kalman's. I solved the questions using other methods, using Gilbert's. Okay, I told you to solve the question using Kalman's. So here, right, I solved one of the questions using Kalman's test, so that you can get a flavor of how to solve it. So I've already like done all the calculations of the matrices, because that will just waste time. So like, so in this question, right, we have to find the controllability and observability of the system for state space representation. So like by seeing this matrix only, we can see this has two Jordan blocks for the same eigenvalue. So obviously this system won't be state space representation won't be controllable or observable, right? These two things we already know. Okay, first rule doesn't follow even here, so that we know, okay, from the start itself. But I want to like solve like this, so that if any other question comes, right, if we have no other option but to solve using Kalman's, you will solve using Kalman's, right? So first I will do two methods. So like this one is like the observability matrix, which is the in the form of C transpose A transpose C transpose A T transpose, and the transpose also. Okay, I will solve for the transpose also, because this is easier to solve. Why is it easier to solve? Because we don't have to take the transpose. So C and A are already given in the equation, just put that here. Else we have to do the transpose and then again solve, so that will be one extra step. Okay, so yeah, that is the reason. So firstly I solved normal q0. Okay, q0 is this one. Okay, I rewrote this actually. This is just a waste of page, sorry. Yeah, here, right, so these are my A matrix, B matrix and C matrix. Okay, so firstly I solved the q0t, because that is easier to solve, right? Q0 transpose. So CA, what is CA basically? C, right, C is 101. Okay, C is 101 and A is this one. Okay, so I calculate the C A, which comes out to be -1 0 -2. Simple, right? 1 times -1, 0 times this, 0 times this, so this becomes -1 plus 0, and then 1 times 0, 0 times this, 0 times this, so this becomes 0 only, and 1 times 0, 0 times this, -2, so this becomes -2 only. Okay, so yeah, this is -2 only. So this is like the CA, right? So this was the second element. First element is simple C only, so it will be only a row, right? So here, right, everything will be a row matrix. Okay, row matrix will come in place. So I will go until 3, right, because n is 3. N is 3, forgot to mention n is 3, because it is 3 cross 3 matrix. So this one will also be 3 cross 3. Okay, 3 cross 3. So So yeah, these things you have to keep in mind. Okay, so now right, so this will be 3 cross 3. I will simply have 3 row vectors, right, row matrices. Okay, so this was the first, I mean the second row. Okay, first row is 1 0 1. Okay, second row is minus 1 0 minus 2, and third row I will do ca square, right? So I don't have to do a square then multiply by c. What I can do, ca square I can write as ca times a, right? So I wrote it here, and I already know ca, right? This is minus 1 0 minus 2, so that you will replace here. This is how you save time, right? So ca, you already write here ca, then you replace with a. Okay, then you multiply, right? Then you get a result. Okay, 104. I'm not doing the calculations. So like this is q not transpose and this is q not. Now tell me, what is the rank of this matrix? Okay, it is up to you. What is the rank? Is the rank 3? No, right? Rank isn't 3, right? Because this whole column is 0, or if you do the normal, like not transpose, then this whole row is 0. Okay, so I can write this in terms of any other of the two, right? So what I can do is multiply 0 with this, so I will get this column, right? So yeah, this is gone. So my rank has to be 2. And are these two related? These two rows related? No, right? These two rows aren't related, because yeah, they aren't related. Okay, so yeah, my rank is 2. Or you can find the determinant. From there you can understand that I'm getting 0. When a whole row is 0, okay, then the determinant is also 0, right? That's simple. So that is also one thing you can do. So from here I can understand my system isn't observable, right? My system isn't observable. Okay, so controllable is up to you only, right? Controllable we have already solved using that matrix method, so that is up to you, that you will solve. So up to this I have done, and this is the q naught transpose. Just remember this, right? So I wanted to prove to you that what I wrote right here, that this is the transpose of this one. So from here you can understand, right? So now I found a transpose. Okay, for a transpose I have to find the transpose of this one. I got it. Okay, and c transpose. Now what happens? This is a 1 cross 3 matrix, right? So this is a row matrix. Okay, now if I take the transpose, what I will get? I will get a column matrix, right? So this will become 3 cross 1. Row and columns are interchanged, right? So this will become 3 cross 1. Okay, so yeah, now right, so what is my q naught? Q naught is this formula, right? I hope you remember 3 times, because 3 cross 3 matrix, and this time what I will get? I will get each column vector, just like the controllability matrix, right? So we get column matrix. Okay, so this will be 1 0 1. Okay, and this will be a transpose c transpose, and this will be a transpose whole square into c transpose, right? So again, simple thing only. So for like this is the c transpose, this is already here 1 0 1, and this is a transpose and c transpose. So a transpose is this one that I calculated here. Okay, as this is a diagonal matrix, right? Diagonal matrix, so its transpose will be same. Okay, diagonal matrix, its transpose will be same. Transpose will be same, right? Transpose will be same. So that is what I'm doing. So I'm multiplying this with c transpose. So what do I get? Simply I multiply, so I get minus 1 into 1, so this will become minus 1, and other 0, so this is 0 only. Then sorry, 1 minus 1 only, and this is 0, this is 0, and this is 0. So this is 0, and this is 0, 0, and minus 2. So I get minus 2 here, right? So I have understanding that what do you mean by 0 0? So I am telling is 0 plus 0 plus minus 2, that I am telling, right? So I hope you know basic matrix multiplication, that I don't have to like do like basics on all those things. So matrix multiplication you should have grip, or when we'll do the mathematics course, there you will have the strong grip, right? There I will absolutely teach you from basics. Okay, so yeah, again, right, I got a transpose c transpose. What I need is a transpose whole square c transpose. So I already have this a transpose c transpose. I will just need to multiply this a transpose once again. I will get this form, right? I will get this form. So again I'm doing that. So what I get? 104, that is the result, right? So I get key 0 as this one. Okay, here also I can see that my rank is 2. Okay, also like you check this one, this is 1 minus 1 1 0 0 0 1 minus 2 4. So here, right, the result that we got, okay, this one was this one 1 minus 1 1 0 0 0 1 minus 2 4. So as you can see, yeah, I was telling the correct thing only, because the transpose of this one is this one. Okay, I mean the transpose of this one is this one only. Okay, so I hope you got the point. Okay, I hope you got the point of how to solve using Kalman's. So just to avoid the calculation time, because this will take a lot of time for calculation, so I skipped the calculation, but I just explain it to you how to solve, because this is just mathematical, right? This is just mathematics, nothing else. Okay, so but how to solve the mathematics, I told you, give you a basic idea. So yeah, so that this is all we did, and this was just this was the basic thing that I needed to tell you before the start of this lecture. So now, right, let's start today's lecture. So today's lecture, the first thing is the principle of duality. What do you mean by duality, right? So like the duality, let's say we have one state equation, this, right? So this is the state equation 1, okay, for the system 1. State equation 1, okay, and let's say this is the state equation 2, right? This is the state equation 2. Now what does the principle of duality say? Before that, let us understand each of these matrices, right? This I hope you already know. This is the system matrix, this is the input matrix, this is the output matrix, right? A, B and C, and this is the state variable, the differentiation of the state variable, and this is the output, right? Now what is this? This is also the differentiation of a state variable, but of the state equation 2 of other state variables. And what is different here is our system matrix is A star. Now what do we mean by A star? A star is this one. The definition of A star is this one. So A star equals to, okay, conjugate, I think it is in bar, conjugate is something like this one, theta. Okay, so what do we mean by A to the power theta whole transpose? So A theta is basically conjugate of A. This is A theta is basically conjugate of A, right? A theta is basically conjugate of A, and A theta whole transpose is the A star. Okay, I understand. So few things I hope you know. Okay, like the conjugate of real numbers, right? Conjugate of real numbers will be the same. Okay, same. So I will give you one example. Let's say my x3 plus j4, right? I will know like this imaginary number, or if you aren't familiar with j, I hope you know iota, you know, right? So now if I want to find the conjugate of this one, right? Conjugate of this one, what will be the conjugate? Conjugate will be the imaginary component will be in the opposite direction instead of the first direction. Okay, it will be 3 minus i4. Okay, 3 minus i4, 3 minus i4, right? So this is what conjugate means, right? We'll just change the imaginary component in the opposite direction, same magnitude but in the opposite direction, the imaginary component. Okay, so now let's take another example. Let's say this is like 6 minus j8. Okay, not j is for electrical people, and I'm like electronics people also, minus i8. So this is y, let's say. So y theta, right? Y theta will become 6 plus j8. Okay, the this one will change, sign will change basically. Okay, simply you can understand the sign will change. Okay, so yeah, this is the main thing. So so now, right now what I was telling is, let's say if my z is only a real number, right, is a 5, it has j like i0. Okay, only a real number, real number, not a complex number. Okay, so what will be the conjugate of this one? What will the conjugate of this one? It will be 5 minus j0. Now minus and plus 0 are same only. Okay, 0 is that magical number, so it's negative, and positive is same, so it will be only 5, right? So from here I can insert like assert that the if z equals to z theta, if z is a real number. Okay, now why is this important? Why is this thing important? We'll see. Okay, so yeah, this is one thing. So what is this? This is A star is A conjugate of whole transpose. So first we are taking the complex conjugate of A. Like what do you mean by complex conjugate? So each element, right, of A system matrix will have like a11, a22, something like that, right? So those elements will be conjugated, complex conjugated. So those element will be done this procedure, right? So yeah, that was the basic meaning. Okay, and my y is b star u, right? Y is sorry, not u. Okay, this is u, this should be z actually, sorry, this should be z. Okay. My y is b star z and this is some u input. Okay, the same input that I'm giving. Now what does the principle of duality say? Basically the principle of duality says, okay, states that if my system 1 is controllable, then my system 2 must be observable, right? And vice versa. So it states that if this system is controllable, then this system will be observable no matter what. Okay, so yeah, as their matrices are related like this one. Okay, matrices are related like this one, that a star will be a theta whole transpose, right? A theta whole transpose. Okay, so this is the principle of duality. Okay, so you might ask like how did this came and where? So obviously I can't give the whole proof, but basic thing one I can give, right? Basic thing what I can give is, so what is the basic thing? Basic thing is like, what is the uh, rank of B A B matrix? Okay, what is the rank of B A B matrix? So let's see. So this time, right, what will be my controllability matrix here? My controllability matrix will be B A B, right? B A B. So so this is also known as like state equation 1 or system 1 also you can say, right? System 1. System 2. Okay, so yeah, this is system 1 and system 2. So now, right, so basically QC1. Okay, what will be QC1? I hope you remember, right? I hope you didn't forget, like it was 2 lectures back. So it is simply B A B. So let's take for order 2 only. Okay, order 2. So this is B A B. Now this is in column format, right? Column format. Now what is my QO1? Not O1, O2. Okay, so what I will do is I will do the transpose thing. Okay, I will do the transpose thing because that is easier for me to find. So QO2, right? What is QO2? QO2 is like column vector only. Okay, we write it like column. So this is C. Okay, C and then here CA, right? But what is the difference here? The difference here is, here we don't have C, we have B star. So I will write B star, right? A is in its place but B isn't, right? Instead of C I am writing B star. So I will write here B star, right? And then okay, why did I go this A, right? I will write this as A star. So this will be B star and A star. Okay, so basically like for the principle of duality to follow, obviously this matrices, right? This matrices have to be related like this one. Okay, this matrices have to be related like this one, right? This A has to be like A star, C has to be like B, C star, B has to be C star, and C has to be B star. Okay, so yeah, this is QO0. Okay, and like now, right, so what is the, now how to find the rank? So rank for this one, let's say I know the rank. Okay, I know the rank of this one. Okay, for this to be controllable, the rank, okay, let me write, for this to be controllable, rank of, okay, let me like this, should be equals to 2, right? So I'm assuming, okay, I'm assuming n equals to 2. Okay, n equals to 2, assuming that, right? Order of the system is 2. Now we know that the rank of this matrix is 2, right? Rank of this matrix is 2. Okay, so let's find the rank of this matrix because this is only like same elements only, right? We have same elements. So what is my B star? So one thing we have to assume is that all ABC matrices are real. Okay, that we have to assume. Okay, else this proof will be very long, we won't go to that proof, but just to get the intuition, right? Assume a real, right? Assume ABC matrix a real. Okay, so then what does my B star and B star A become, right? So like B star is simply the conjugate of transpose, but what I told you is that if my number is real, then the conjugate will be equal to the number itself. So B star will be equal to B itself. So I'll just have to do transpose of that. So this will be B transpose and this will be uh, B transpose A transpose. Now what I will do, I will just flip them, right? I'll just flip them. Okay, I'll just flip them. I will take the transpose of the whole equation, right? So QO2 whole transpose of whole transpose. This becomes B transpose A transpose, right? So I will take the transpose of this one. So again, right, I will follow the rule of transpose. So this is B transpose A transpose, okay, whole transpose. So this becomes QO2. This transpose cancels out and this becomes B, then A B. Now is this thing familiar to us? Yes, this thing is familiar, right? BAB. So but we know the rank of this one. Rank of this one is, we know the rank. We know, so from 1 I can do this like equation 1 from 1. Okay, from 1 we can say that rank of QO2, right? Rank of QO2 will be equals to 1. Okay, rank of QO2 not Q, yeah, rank of QO2 will be equals to 1, right? Sorry, not 1, sorry, I'm sorry, it will be 2, right? Okay, it will be 2 because these matrices are same only, right? So it will be 2. Now if my rank of QO2 is 2, which is equals to n, full rank, it is full rank matrix, then what does it mean? My system is observable. This means system is observable, right? Okay, my system is observable. Okay, so yeah, this is the basic meaning of this principle, right? Principle of duality. So just remember this: if like the matrices are related like this one, okay, then principle of duality will follow that if like one system is controllable, then the other system will always be observable and vice versa. Okay, so yeah, this was it basically. So now we'll go to another theoretical point, which is stabilizable systems and detectable systems. So what is stabilizable systems? Like we have already, I've told you already while studying the controllability, basically, right, if my state space representation has few states which are unstable but controllable. Okay, I told you, right? Like few states are not measurable, but those states are already stable, right? Those states are already stable, so we don't need to make them stable. As they are already stable. Those eigenvalues are already negative, so that's fine. But few eigenvalues aren't negative, but we are able to measure those states, right? We're able to measure those states, so that is my advantage. So I will change the eigenvalues of those, I will make them negative, so that will make my system stabilized, right? Because already those uncontrollable state variables were not measurable, but those were already stable. But the controllable state variables were not stable, but with the help of controllability, with the help of the input and some feedback, I can make them stable. So then my system will be stable, right? Okay, like my system will be stable. So those are called as stabilizer system, right? Those are called basically stabilizer systems. Okay, so and these, right, if my state space representation has few states which are stable, okay, but uncontrollable, then those are known as unstable, like unstabilizer systems. Okay, or those are known as unstabilizer systems. So like, just hold on a second, which are, it will be like which are, okay, which are unstable but controllable. Okay, so yeah, yeah, this is basically the thing. Okay, I told both things, so that is okay, right? That is okay. If my state field representation has few states which are stable but uncontrollable, that is fine. Then the system is stable, like stabilizable, because the system is already stable. Okay, the uncontrollable state variables are stable, that is fine, and the controllable state variables are unstable, but we can make this stable. Hence this type of system is known as stabilizable systems. Okay, so remember this there is and there. Okay, there is and there, just keep that in mind why there is and. Okay, now what is my detectable systems? If my state variable state space representation has few states which are unstable, so it has few states which are unstable but they are observable, right? Okay, but they are observable. And also if my state space representation has few states which are stable but unobservable, what will happen? If I can observe these unstable systems, then I can give it back to the input, which can make it controllable, like which can again stabilize the system, right? If I can observe the unstable state variables. Okay, that's why this is not a detectable system. That is not an issue. Also, and other condition is if my system has state variables which are stable but unobservable, that is fine now. If the states are already stable and I am not able to observe them, that is fine. Okay, because it is already stable, right? I don't need to change anything to that, right? So yeah, that was the thing. But what was the issue? What would have been the issue? Like if my system has few state variables which are unstable and unobservable, then I have an issue. Okay, then I have an issue. How? I won't be able to observe those states and make them stable, right? I have to make them stable. The final aim of my control system is make my system stable and get a desired output, right? So I can't make them stable, so then that won't fall under this category. Okay, also in this category, if my system has few states which are unstable but are also uncontrollable, then also my system won't be stabilized system, because I won't be able to stabilize them, right? So my input can't measure those unstable states and I can't be able to give feedback, and then I won't be able to stabilize those system. Okay, so yeah, basically it is this thing only. Okay, so these are stabilizer systems and unstabilized systems. Okay, so yeah, now right now we'll do few questions. Okay, so let's start the question basically. Oh yeah, this is the first question. So this is a gate question basically. So what is this question tell us? So we have been given the state space equation of a system is described by this x dot ax plus bu. Okay, and this we know already, right? And this is x is a state vector, u is input, and y is output. Now a is this, b is this, and c is this, right? A, b, c are this. Now we have to find the transformation. Very easy, right? Very easy. So first method is homework for you, is simply the formula. What was the formula? It was si minus e inverse, right? No. Like if you said yes, then you, like you, yeah, what I do, I'll scold you, or I can even come to your screen, right? So what was the formula? The formula was c times si minus a inverse, right, times b. Also don't forget the b also. There was a plus d also, but that d is most of the cases 0. Okay, so yeah, remember this, right? This is very important formula. So this is my transfer function. Okay, this is my transfer function. So yeah, like you solve with this formula. Now I will solve using second method. What was the second method? Second method, right, using, like, what I observe is this is some standard form. What standard form is this? Okay, what I see, this is b is in standard form and this a also is in standard form, right? Like a diagonal matrix, right? So basically, and I have one above, so like for 2 cross 3 this is 0 1, then you remember, right? For 3 cross 3 it was 0 1 0 0 0 1. Now numbers were in the last row. This is a CCF format, right? Controllable canonical form. So this is a CCF form. Okay, now this is CCF form. So what I can do, I can write the ABC, and from there I can directly write the transfer function. So yeah, let me write the ABC basically. What is my a is 0 0. Okay, 0 0, and this is 1 minus 2. This is b. Okay, 0 1, and this is c 1 0. Okay, So this is ABC, right? Now, right, like we can see what is the order of the transformation. It will be my order of the A matrix. It is order 2. So there will be 2 integrators and there will be one square term, right? So now basically what I will follow is I will go like this one, right? I hope you remember. I will remember. I used to mark arrows. I go like this. Okay, if you don't like, let's practice this. I will go like this and I will go like this, right? I will go like this. Okay, so basically, right, what will happen? So these means the coefficients. This is the coefficient of s to the power 0. This is the coefficient of s to the power 1. Okay, and I will have a square anyways there. Okay, a square will be there anyways. Okay, now what is the coefficient of this one? This will be the coefficient of s to the power 0 and this will be the coefficient of s to the power 1. Okay, so I hope you remember, right? This is the numerator and this is the denominator. Okay, so my T of s, right? This is a trick formula. Okay, obviously you can use the formula. This is a trick that will give you the answer very quickly. Okay, we'll use this trick in the next few questions also. From there you will understand. Y of s upon u of s equals to y of s upon u of s equals to, it is basically, right, y of s upon u of s, simply the numerator is what? This is s to the power 0 and this is s to the power 1. So s to the power 0 times 1 plus 0 times s to the power 1. I am writing all this just to explain this to you, but you will write this very quickly, right? So now a square will come. Okay, a square will come along with this and we'll start from here, right? We'll start from here. Okay, this will be my coefficient of s to the power 1 plus 0 times s to the power 0. Okay, this 0 will be my coefficient of this one. Okay, and this minus 2 will be coefficient of this one. So this is how you remember, right? You go from here, but while starting, right, you go from here. Okay, while starting you come from here, right? You come from here, so this will be 0 and this will be minus 2. That's how you remember, and this will always be 1. Okay, 0, minus 2 and 1. Okay, so yeah, so this is my transformation. So let me simplify this one. Okay, simplify this one. This is basically this is 1 divided by s square minus 2s, right? 1 divided by s square minus 2s. So I will take the s as common. Okay, so my transfer function will be 1 by s into s minus 2. So s into s minus 2 is like this one, right? So it is D option. Okay, so my answer will be simply D. So let me mark this one. Okay, so yeah, this was very simple, very easy. You could have done with that formula, but just to get you started off with. Now, like this one is also easy. Okay, so write the state space representation for the following transfer function. Also draw the state space diagram, right? So we have to do all these things. So like firstly check like state space representation we have to write. So nothing has been said, right? Nothing has been said. Okay, this is just like a theoretical question. So what I will do is I will use the CCF form. Okay, so CCF form is very easy. You could have done the parallel decomposition of diagonal form also, but I will do the CCF form only, right? So diagonal form is nothing, just a one first order, right? So it is nothing. So using CCF form, what is CCF form? It is controllable canonical form, right? CCF form. So my CCF form, right? For CCF form, my transfer function is given like this one, right? U of s equals to 100 by s inverse, right? I multiply the highest power in the like with the inverse. Okay, or take the common of the highest power. Okay, then what I do is multiply this dummy state variable x naught of s and x naught of s in both numerator and denominator, and then we draw a state diagram or write the state equations. But before that, like we know the order is 1. Okay, so from here also we can like this is also important. to understand what will be the order of A, okay, and what will be the order of B. These things also you should remember, right? Sometimes this also helps in matrix calculation or in option elimination, right? So in option elimination, by just seeing the order, you can eliminate that particular option, right? So this also I will revise you a bit, okay? What was the order of B? What was the order of C? Okay, tell me what was the order of A? Order of A was n cross n only, because it is the order of the system, okay, and it is called system matrix, that is why. Okay, now what is the order of B? Order of B was n cross n, right? It was n cross m. It was B multiplied by U. Always, if you forget, right, you write the state equation, right? You write the state equation. From there you will always remember it. So what was state equation? It was x dot ax plus bu, right? And y was equals to cx, right? So what will be my order of A? Order of A will depend on the x, right? So for x, the number of whatever the number of rows is, and for A, number of columns should be equal. So it should be n, right? Okay, and what should be the number of rows of A? Number of rows of A will depend on number of rows of x dot, which is n again. So it will be n cross n. Like this you remember, right? Like this you remember. Okay. For B, right? Bu. So what is U? U is a column matrix of m cross 1, right? M cross 1. So the number of columns of this B will be m, and number of rows will be n due to this one. Okay, the first number of rows is fixed due to this one of all of these matrices, okay, of A and B, but the number of columns will vary depending on what it is multiplied. Okay, so this is A, B and C, and C is again what? C is P cross n, right? C is P cross n. Okay, so yeah, this was A, B and C, and from here, like, our n is only 1, okay, and our m is only 1, because it's a CSO system. Okay, so A will be 1 cross 1, okay, A will be single element, B will be single element, okay, and C also will be 1 cross 1. Okay, so yeah, these things are also important to eliminate the options. So these things you should keep in mind. Okay, so like from here, order of the system, I'm doing just one question very formally, so that all these things you keep in mind for every question, right? For every question. Okay, so yeah, this is the order of system. Now let me draw the state diagram, right? So we have to draw the state diagram. Okay, state based representation also we have to write. So I can write from directly here also, right? What I can write is, like, you're pro at this right now. So this is simply my x dot matrix, and this is my A vector, right? And this will be a single element, okay, single element only. And what will be it? It will be simply -3, because this x naught into -3 will go up this side, and this will be -3. Okay, still I will write the equations. From there you will understand. Okay, let me write the equations, else you will get confused again. So let me take another page. So I need to equate the numerator with this one, and equate the denominator with this one, right? So y was equals to x naught of s, and x of s equals to, oh sorry, not x of s, sorry, this was c of s, right, equals to 1 plus 3 s inverse of x naught of s. So x naught of s equals to u minus 3 s inverse into x naught of s itself, right, plus u. So from here you can write the state equation, or first you can draw the state diagram. From there you can write the state equation. This is already done, like, I think multiple times, but still, just to like give you a bit of revision at the ending stage. So I will give you a revision, because this chapter has gone very long, right? So there will be only one integrator. Okay, what will be the gain here? It will be this one, right? This one, this is, what is this? This is x naught of s, this is s inverse x naught of s, right? And what is this gain? This is 100, right? This is 100, right? And this is 1 by s. Now we have a feedback also. Take a feedback also. If I take a feedback, right, feedback is this one, right? This is -3, okay, and this is 1. Okay, so like this is 1 only, right? This u of s is 1 times this, so this is u of s, and this is what? This is y of s, right? This is y of s. Okay, so now what you can do to write the state space equation? like either you can go from here directly, or what you can do is like solve like what do you say, from the time domain expression, right? So what you do, you copy this one and convert this into time domain expression. So again, those procedures are there, right? So remove the initial state variables and all those things, those are there. So here initial equations are not here, so I will remove this, I will remove this. Initial conditions are not here, so this will become my x1. This will become my x1 dot. Okay, so my x1 dot is equals to what? It equals to some 1u and minus 3 x1. So this will be minus 3 times x1 plus 1u, right? So it is 1 only. And what is my y equals to? Y equals to 100 times x1. So it is 100 times x1. Okay, like this you can solve. What is the other method you can solve? Okay, the other shortcut method is simply by the transfer function. So we have the transfer function, right? Or the transfer function. So what is the transfer function basically tell us? So if I go from grow from here, right? If I go from here, so I have to start the matrix from the right hand side, and as it is only one element, so my x dot, right, x dot will be equals to minus of this one. So the sign changes, right? I hope you remember the sign changes. So it is minus of this one, okay, and this is x only, plus u is only 1 1 0 0, like no, 0 1 1, and like the last element is always 1, right? So only if it has one element, that will be 1. Okay, so as it has only one element, it will be 1. So I hope you understand, right? So if in the previous case we had two elements, so it was 0 1, so the last element was always 1, so that's why this will be 1 only. You will not go, okay, because this is a controllable system. Like we're converting into controllable canonical form. That like that also you can remember that it has to at least have some component of u, right? Okay, for it to be controllable, as we have only one state variable. Now y, right? Y, what will y will be the upper portion. So again, I will go from here. I have only one element, so it will be 100 only. Okay, in the next example we will understand bit better. Okay, I will start from here. Okay, so what is the coefficient of this one? The coefficient of this one is s to the power 0, and the coefficient of this one is also s to the power 0. So which will come over here, right? So yeah, like I'm going the opposite direction. Previously from the state space representation I went to the transfer function, and from here I'm going like this. Okay, so now we have another transfer function, okay, in this question, and we have to write the state space representation for the following transfer function. I also draw the state space diagram. So again the same thing, right? But this time it is a second order system. Okay, so how to solve a second order system? So again, right, what is the order of the transfer function? You can do this very fast, but I will do this slow for you. Order of transfer function. Okay, I will write everything, all the information is true. So also, what is my like input output is a CISO system, right? It is a CISO system. Okay, so what will be my m1, p will be 1. So again, right, what will be my order of a will be n cross n, so it will be 2 cross 2. What will be my order of b will be my n cross m, right? So it will be 2 cross 1. Okay, now what will be my order of c? So c, right, c will be basically this, and that is also, so it is 1 cross 2. Okay, c will be 1 cross 2. So yeah, these are basically my orders of the matrix, and if options are given from there also, you can eliminate this. Okay, you can eliminate this. So yeah, this is basically orders. Now let's solve for the circuit. So like not for the transfer function. So we can do this using two methods. First I will do the lengthy one. Okay, so lengthy one is convert this into CCF form. Convert this into CCF form, that is controllable canonical form. So how will I convert? I will copy the transfer function, right? I will copy the transfer function. So the transfer function, right, I will multiply the highest power, okay, take common the highest power, sorry, take common the highest power and keep it at the top, right? So here highest power is s to the power 2, so s to the power 2 will go in the top, so it will be 10 s to the power minus 2, then this will be 1 plus 5 s inverse, okay, plus 10 s to the power minus 2, okay. So yeah, this will be my transfer function, right? So now what I will do, I will multiply the dummy variable, right? So I'm doing this fast because we already know all this, right? We're just solving this. So if I multiply the dummy variable, this is x naught of s and this is also x naught of s, right? Okay, so again, right, we have to draw the state diagram, or you can solve the transfer function first. Sorry, you can write the state equation, but first I will draw the state diagram, right? So I will do this directly now. Okay, so just bear with me. So if you understand, that's good. If you don't, that's not my fault because you haven't watched the previous lectures. Okay, so here we have two indicators, order is 2. So for controllable canonical form, we draw it like this. We draw a straight line first, okay, draw a straight line first, then we write the indicators. Now for indicators, right, what I used to do, like what I do is I put a gain of 1 between the two state variables, different state variables, just to tell that my x1 dot will be equals to x2. X1 dot is coming, like, sorry, x2 is coming into x1 dot, okay. So x2, okay, and this is one base, and this is like, okay, now we know we have two integrators. Now I don't know here again, this is input and this is my output, right? This is input, my output. I know this is my x1 dot and this is x2, and this is like, this one was supposed to be x1 and this is my x1 dot, okay, and this is supposed to be my x2 dot, right? So now, right, now what will happen? Now what do I know? So this dummy variable is multiplied. I will equate this with u of s, okay. So if I write here, right, one thing I will write, like, let me do one thing. If you don't understand the state variables, first I will write the x naught. So where will my x naught be? As, right, x naught is related with u, right? Here x naught with itself is not present. There is always one s term in front of it. Only x naught is present over here, okay. So I will write my x naught here. Like, I'm just playing with the reasoning, or you just remember that x naught will come at the input side, okay. We'll remove this x naught after our state space diagram is complete, okay. This is a dummy variable, so this is x naught. Now what does this become? This becomes s inverse x naught, right? And what does this become? This point becomes s to the power minus 2 x naught of s, right? So this becomes x to the power minus 2 x naught of s, okay. So now I written it. Now I will write the equations, okay. Relate this with u. So for u, right, I will only use x naught of s here, and all the other terms will go into the u side, okay. Then this one will be with the negative sign, right? So firstly, u of s is there in x naught of s, so u of s is there, and what is the gain? Gain is 1, okay, as this is 1 and this is 1 also. The coefficient of u is 1, okay. So here, right, the gain will be 1, okay. And now what is happening? This 5 is going over there, and this is becoming minus 5. So minus 5 s inverse of x naught is also equals to x naught of s, okay. So let me write the equation if you can't understand, because see, some people may get confused, but I've already written it multiple times. So whoever understood this, right, you solve this quickly, okay, solve this quickly. But whoever didn't, so for you guys, I'm writing the equation. So this is u of s equals to, I'm just equating the denominator, right? U of s equals to this one, right, 1 plus 5 s inverse. So it is 1 plus 5 s inverse plus 10 s minus 2 into x naught of s, right? So this one, x naught of s equals to u of s. U of s is there. This one becomes minus 5 s inverse of x naught of s, and minus 10 s inverse s to the power minus 2 of x naught of s, and like plus u of s is already there, right? Plus u of s is already there, okay. So right, so basically from here you can understand that this x naught of s is here is equals to minus 5 s inverse times x naught of s. So S inverse of x naught of s here, so I need to give a feedback of -5, right? So if I can give a feedback of -5, this will come out to be like this, okay? And where is my, this is S inverse of x naught of s, and this is my s to the power -2 of x naught of s, which has -10 of gain, and which is also coming into x naught, right? So here is minus s to the power -2 of x naught of s. So this one will also come into x naught, right? This one will also come into x naught. Oh, sorry, this one has a gain of -10, right? This one has a gain of -10, okay? So yeah, these are basically two components, right? These are basically two components, okay? So yeah, now I got the state space. Also I have to write this output equation also, okay? So I will delete this now just to explain you. I wrote all this, so this is just a mess, okay? Now the output expression is this one, right? 10 times s to the power -2 of x naught equals to y. This is simple, straightforward, right? So this is my s to the power -2 of x naught of s. I have to multiply 10 with it, so I will multiply 10 and I will get my output, right? So that is fine. So now what I will do is I will remove this dummy state variable, okay? Dummy state variable. I will remove the dummy state variable, and my state space equation is ready, okay? My state space not equation, my state space diagram is ready, right? So like I can name this as x1, okay? Always for CCF, my convention is to name this as x1 dot, then this one as x2, sorry, x1, this one as x2, and this one as, sorry, x2 dot, and this one as x2, right? So my convention is this one basically. Sorry, now focus. Sorry, I missed one thing. The convention was this one, sorry. So as u like 0 0 1, right? So 0, if like the matrix is 0 1, then this input should be related with the x2, sorry. So I messed up here. It should be x2 x2 x1 x1. So this is my convention that I follow, right? You have seen me like in the previous examples also. So yeah, okay, one thing I messed up here, like what, yeah, this was supposed to be s inverse s to the power -2, okay? Yeah, this is correct only. Yeah, this is correct only, right? So okay, so now let's solve the like this one, okay? Let's solve the using transfer function, right? Let's solve using transfer function. So how will I solve using transfer function? Okay, did I miss something? This was 10, was it 10? Okay, this was 10, okay. So if I solve using transfer function, what do I get? So my transfer function, right? If I copy the transfer function, something has been messed up. কিছু মিস করেছি কি? I don't know. 100 notes. জাস্ট আমি স্পেস দিয়েছি বলে এখান দিয়ে যেত, এখান দিয়ে যেত, পুরো পর পর যেত, দুটো তো ওখান দিয়ে যেত। এটাতে কী ঘটেছে আমি এটাই বুঝতে আরে পোকা তো সেম পয়েন্টে নিয়ে নিয়েছি। Okay, from here we can write the state space equation, but from the transfer function also we can write the state space equation. How? Let us see. So my transfer function is simply equals to this one, right? So I will copy this one. I will copy this one, okay? Now if I copy this one, right, so I will move like this one. So what will be the this coefficient is s to the power 0. This will be my first like my first element, right, in negative sign basically, and this will be my second element in the A matrix of the last row, right, last row, and this will be my new method, and we will go like this one only. We'll go like this one only. Okay, so my direction will be like this one only. So yeah, now let's solve it. There you will understand. So this is a standard form. Okay, standard form I'm solving. So this is my x dot. Now my what will be a will be 0 1, then last row will be like this one, as this is a 2 cross 2 matrix, right? Only 2 rows. So I will move from here, but I will move from here, right? And in negative sign. Okay, I will oppose the sign, right? So first I'm getting 10, so I'll write minus 10 here. Then I'm getting 5, so I'll write minus 5 here. Okay, now I will have the x matrix here. Okay, plus what else do I have? I have the B matrix. So B matrix is simply 0 1. It is standard form only, times u. Okay, 0 1 times u. Okay, now what is my Y matrix equals to? My Y matrix, right? Y matrix equals to simply this one only, right? This one. Okay, so it's basically we have two elements, right? It is 1 cross 2, right? As I mentioned, 1 cross 2. So we have two elements. So this one I will start with, then I will get 0, because my s to the power like s to the power 1 has power like multiplied by 0. Okay, and the coefficient of s to the power 1 comes at this node, right? At this point. Okay, it goes from increasing, the coefficient increases. So here the coefficient of s to the power 0 comes, which is 10, and here the coefficient of s to the power 1 comes, so 10 0. Okay, so yeah, this is 10 0, and yeah, this is my Y matrix basically. I mean, this is my C matrix, A matrix, and B matrix. This is my state space representation. So I hope you understand, right? I'm going from here, and this, right, this will go from here to here. Okay, and for this one also I will go from here to here, but no sign change. No sign change. This is just for remembering. This is just trick. Okay, nothing else. Or you do it from here, right? Do it from here. So like you remove the 1 by s. Okay, then you write the x1 x1 dot in terms of x2 and x1, and x2 dot in terms of u and x2. Okay, like that you solve, and you will get to the same. We have done this multiple times. Okay, so in this lecture, right, we haven't done any new questions. Okay, so that is unfortunate. Okay, but in the next lecture we'll do few new questions. Okay, like which we haven't done. This one is basically just a revision session, because the chapter has gone very long. Okay, just to keep everything in your head, right? Whatever we did, right? So yeah, this one was this matrix. So I get my like ABC matrix I get. Okay, so in the next lecture we'll do more questions. Okay, so I think yeah, for this lecture this is enough. I had to make another lecture, sorry for that. So next lecture will be the last lecture of the state space, and yeah, I will give you a brief overview of the whole lecture, right, of what we did throughout the whole chapter, basically state space chapter. Okay, so I will try to give you a full revision of the state space, basically overview. Okay, yeah, thank you for watching.